You ever look at the world and feel like it's all just a big, chaotic mess? Well, what if I told you it's actually running on a surprisingly clear set of rules? Today, we're going to crack open the user's guide to reality itself. We're using this physics textbook as our map to learn the universe's fundamental language. So let's kick things off with a little puzzle. Think about the GPS that gets you to that new coffee shop, the wild physics in a video game that make a car crash look real, and a giant skyscraper that doesn't fall over in the wind. What on earth do those three things have in common? They seem totally unrelated, right? But they all share a fundamental, hidden secret. And the answer is, they're all designed and built using a hidden language of rules, the language of physics. It's all about measurement, it's about numbers, and it's about understanding how our world works in a way that we can actually predict. To speak any language, you have to learn the words first. And in physics, those words are called physical quantities. This is our first big step, our ground zero for figuring out how scientists actually describe the universe. So what even is a physical quantity? Well, it's basically how we stop describing the world with vague feelings and start using cold, hard facts. Instead of just saying something is hot, a physicist says it's 100 degrees Celsius. It's the huge difference between a simple observation and an actual measurement. But here's the cool part. You don't always need some fancy lab equipment to get a measurement. Sometimes the best tool you have is your own brain. And that's where estimation comes in. Now, this isn't just a wild guess. It's an educated one. It's looking at a room and thinking, yeah, that's probably about 20 feet across. It's about building an intuition for the numbers that describe the world all around us. And this is where things get absolutely mind-blowing. Just look at the insane range these numbers cover. We can use this same unit, the meter, to talk about the height of a kid, which is about, 1 meter, and then zoom all the way down to the size of a proton. That's a decimal with 14 zeros. And then we can zoom all the way out to the edge of the observable universe, which is a 1 followed by 26 zeros. It's just incredible. That's the power of this language. Okay, so we've got our numbers, but are they the right numbers? And if we do it again, are we going to get the same number? This leads us to two super important ideas in science: accuracy and precision. They sound kind of the same, I know, but trust me, the difference between them is absolutely crucial. The easiest way to think about it is like a game of darts. Accuracy is all about hitting the bullseye. It's how close your measurement is to the real, true value. Precision, on the other hand, is all about grouping. It's how close your throws are to each other, even if you're nowhere near the center of the board. And this image just nails it. Look at dartboard A. All the darts are clustered right in the middle. That's the dream, right? That's both accurate and precise. Now look at B. The darts are in a really tight little group, so the throwing is super precise, but they're way off target, so they're not accurate at all. In science, you always want to be A, but B is a huge clue that something with your equipment is consistently off. Because no measurement is ever 100% perfect, scientists have to be honest about that. And that's where this idea of uncertainty comes in. It's that plus or minus you always see with measurements. It's not a sign of failure. It's actually a statement of confidence, saying, hey, we're really sure the true value is somewhere in this tiny little range. Being honest about what you don't know is what makes science so trustworthy. All right, so far we've been talking about things that are just simple numbers, like how much something weighs or how much time has passed. But what happens when a number alone isn't the whole story? What if you also need to know which way? This is where a totally new, powerful idea comes into play: the vector. This picture is just the perfect example. If someone tells you that your destination is 10 kilometers away, well, that's pretty useless information, isn't it? You need to know which way to go for 10 kilometers. That combination, the distance and the direction, that's a vector. So that gives us our two main categories. A scalar is just the number. How much? Like 80 kilometers per hour. Or 10 kilograms. But a vector is the number plus a direction. How much and which way? So it's not just 80 kilometers per hour, it's 80 kilometers per hour north. That little bit of extra information, the direction, is a total game changer. So why does this one little detail, direction, matter so much? Well, it's because vectors are how we analyze all the complicated movements and forces happening in the real world. They give us a special toolkit to break down really messy problems into simple, easy-to-solve pieces. And right here, this is the physicist's secret weapon. See that diagonal arrow? It represents some kind of force pulling at a weird angle, which is really hard to work with. So the genius move is to break it down. We just pretend it's actually two simpler forces, one pulling straight to the side and one pulling straight up. And just like that, instead of one complicated problem, you've got two super simple ones. It's the ultimate divide and conquer strategy for physics. And that brings us right back to where we started. Remember the GPS, the video game, and the skyscraper? What's their secret? It's vectors. Your GPS is constantly calculating your position vector. Video game developers use vectors to make everything look realistic. Engineers use force vectors to make sure a building can stand up to the wind. This whole language of size and direction isn't just stuck in a textbook. It is literally running the modern world. So there you have it. We've learned the first few words in the language of reality. What physical quantities are, the critical difference between accuracy and precision, and the amazing power of vectors. And these aren't just ideas for a science lab. They're tools for thinking more clearly about everything. So the only question left is, now that you know some of the rules, what part of your world are you going to see a little differently?